Welcome everyone. I'm excited to introduce today's presentation on the Introduction to Corrosion Test. We'll explore how these tests evaluate the resistance of stainless steel to corrosion and their role in detecting sensitization and intergranular attack. Over the next few slides, we'll cover the key concepts and importance of corrosion testing in material analysis. Let's get started. Let's take a closer look at the test standards on this slide. First, we have ASTM A262, which is specifically designed for intergranular corrosion testing. This test helps us determine how susceptible stainless steel is to corrosion along the grain boundaries. It's a crucial step in ensuring the material's durability in harsh environments. Next, there's Practice A, known as the Oxalic Acid Etch Test. This is a rapid screening method used to evaluate the microstructure of stainless steel quickly and efficiently. It involves electrolytic etching in oxalic acid, which reveals the microstructure condition of the material. The key point here is that this test provides a visual indication of the microstructure, helping us identify any potential issues such as sensitization or segregation. Overall, these standards and practices are essential tools in quality control, ensuring that stainless steel components meet the required performance standards before they are used in critical applications. Let's walk through the principle of this test. First, the specimen is etched in a 10% oxalic acid solution. This etching process helps reveal the microstructure clearly. Then, we apply an electric current for a fixed period of time. The purpose of this is to encourage the corrosion process at specific sites. Under the microscope, we observe the grain boundary attack, which indicates how the material responds at the microscopic level. This method is useful for understanding the material's corrosion resistance, especially at the grain boundaries, which are often more vulnerable. It ties back to our overall theme of evaluating material performance and integrity in different environments. Let's take a look at the test solution we used. It consists of 10% oxalic acid by weight. This means that for every 100 grams of solution, 10 grams are oxalic acid. We prepared this solution carefully using distilled water to ensure purity and consistency. Using distilled water is important because it helps us avoid any impurities that could affect our results. Overall, this test solution is a crucial part of our process, helping us achieve accurate and reliable measurements in our experiment. Let's take a closer look at the test equipment we'll be using in this setup. First, we have the DC power supply, which provides a stable and controllable source of direct current, essential for maintaining consistent conditions during our experiment. Next is the electrolytic cell, the core component where the actual electrochemical reactions happen. The specimen itself acts as the anode, meaning it's the electrode where oxidation occurs. It's crucial to observe how it interacts within the cell. We also have the microscope, which allows us to closely examine the specimen's surface and any changes that take place at a microscopic level. Together, these tools enable us to conduct precise and insightful analysis of the electrochemical processes involved. This equipment setup is fundamental to understanding the behavior of materials in electrochemical environments, which ties back to our overall theme of material performance and durability. Let's talk about specimen preparation. The key here is that the surface must be mirror polished. This step is crucial because a smooth, reflective surface ensures that we can accurately analyze the specimen later on. Any imperfections, like scratches or contamination, can interfere with our results, so it's essential to make sure the surface is free from these issues. Remember, taking the time to properly prepare your specimen will make a significant difference in the quality and reliability of your analysis. This step connects directly to our overall goal of achieving precise and accurate measurements, so don't rush through it. All right, let's walk through the testing procedure. First, you'll want to take your specimen and give it a mirror polish. This step is crucial because a smooth surface ensures more accurate and consistent etching results. Next, measure the total immersed area of the specimen that will be etched. Make sure to record this in square centimeters, as this will be important for setting your etching parameters. Then, connect your specimen as the anode in the electrochemical setup. You'll etch it at a current density of 1 ampere per square centimeter for about 1.5 minutes. This precise control helps us achieve a uniform etch and reveals the microstructure clearly. After etching, rinse the specimen thoroughly, first in hot water to remove any residues, and then in acetone or alcohol to clean the surface and prepare it for examination. Finally, examine the etched surface under a metallurgical microscope, ideally between 250x and 500x magnification. This allows us to observe the microstructure details effectively. This step is essential because it helps us analyze the microstructure's features, which tie back to our overall goal of understanding the material's properties. Let's take a moment to watch this video, as it will help us understand the key points more clearly. What you're about to see highlights the practical application of the concepts we've discussed so far, making everything more tangible. Pay close attention to the details and how the ideas are implemented in real-world scenarios. This visual will reinforce the importance of integrating these strategies effectively. Remember, understanding these examples is crucial because they connect our theory to actual practice. So, let's watch and observe carefully how these principles come to life.
Take the specimen and mirror polish. Measure the total immersed area of the specimen to be etched in square centimeters. Connect specimen as anode and etch at 1 ampere per square centimeter for 1.5 minutes. Rinse the specimen thoroughly in hot water and then in acetone or alcohol. Examine the etched surface on a metallurgical microscope at 250x to 500x.
Let's take a closer look at the microstructure, specifically the step structure. When examining the grain boundaries, you'll notice they are smooth, which is a very positive sign. Smooth boundaries typically indicate good material quality and proper processing. You'll also see that there is no attack along these boundaries, meaning that there are no signs of corrosion or deterioration in this area. This is crucial because it shows the material has maintained its integrity and hasn't been compromised. Overall, the condition here is acceptable, which means that the microstructure is within the desired parameters for this particular application. Recognizing these features helps us assess the overall health and durability of the material, connecting back to our broader theme of ensuring material reliability and performance. Let's take a closer look at the microstructure, specifically the dual structure. Here, we see a partial grain boundary attack, which means the corrosion or degradation has affected the grain boundaries, but hasn't completely compromised the entire structure. This is something we can consider acceptable in certain situations, but it does require caution. It's important to monitor these areas closely because, over time, they could develop into more significant issues if not properly managed. Overall, understanding this dual structure helps us better assess the material's condition and determine the appropriate maintenance or intervention strategies. It ties back to our overall theme of ensuring material integrity and longevity. Let's take a closer look at the microstructure, specifically the ditch structure. What we're seeing here is a continuous grain boundary attack, which is a key indicator of sensitization in the material. This means that the grain boundaries have become more susceptible to corrosion or degradation due to the local chemistry changes. Importantly, this condition is actually rejected, meaning it's not the ideal or desired state for the material. Recognizing these features helps us understand how the material may perform under different conditions and guides us in making improvements. Overall, identifying such microstructural signs is crucial in assessing material health and ensuring reliability in our applications. So let's talk about what sensitization actually is. Sensitization is a process that becomes necessary when we're dealing with specimens where it's difficult to reveal the microstructure, mainly because there's a lack of chromium carbides. Now, chromium carbides play a crucial role in corrosion resistance, so understanding how they form and their behavior is key. This process involves a specific heat treatment, typically around 700 degrees Celsius, and it's usually done for about 30 minutes. During this heat treatment, chromium carbides form at the grain boundaries, which is a critical point. However, this formation causes chromium to deplete at these grain boundaries, meaning there's less chromium available there. And this depletion can lead to increased susceptibility to corrosion, which is a big concern in many applications. So, in essence, sensitization is a controlled heat process aimed at understanding or managing the microstructure. But it also highlights the delicate balance between beneficial carbide formation and potential corrosion vulnerabilities. Today, I want to talk about some of the key applications where these materials really shine. First up, austenitic stainless steels, like 304, 316, 304L, and 316L. These are incredibly popular because of their excellent corrosion resistance and mechanical properties, making them ideal for a wide range of industries. You'll find them used extensively in food processing, chemical industries, and even in architecture. Next, welded components are another major application area. These steels are often chosen because they can be easily welded and maintain their strength and corrosion resistance after welding, which is crucial for constructing durable, long-lasting structures and equipment. We also see these materials used in heat-treated forms. Heat treatment can enhance their strength, toughness, or other properties depending on the specific requirements. This flexibility makes them suitable for components that need to withstand demanding conditions. Overall, these applications highlight the versatility and reliability of austenitic stainless steels across various sectors, reinforcing their role as essential materials in modern engineering and manufacturing. Keep in mind that proper polishing is absolutely critical to achieving the best results. It might seem like a small detail, but it really impacts the quality of the final product. Controlling the current density during the process is also key. Too high or too low can lead to issues, so precision here makes a big difference. Avoid overetching, because that can damage the material or create unwanted features. To ensure we're on the right track, always compare your work with reference images. We use these as benchmarks to guide adjustments. These points all tie back to the overall goal of maintaining quality and consistency throughout the process. Thank you for watching. I truly appreciate your time and attention today. I hope the information shared has been insightful and helpful in understanding the key concepts we've discussed. Remember, the ideas and strategies we've explored are all about making a positive impact and driving meaningful change. If you take away anything from this presentation, I hope it's the importance of staying engaged, curious, and proactive in applying these concepts. Thanks again for being such an attentive audience, and I look forward to connecting with you all soon.